When you plug your phone in or turn on a light, you probably just think about the 120 volts coming out of the socket. But behind that simple plug is this incredibly elegant and powerful system that keeps our entire world humming. Today, we're going to pull back the curtain on the invisible force of three-phase power and find out why the number 3 is the absolute secret to keeping our modern world running.
So, to really get why 3 is the magic number, we have to start at the very beginning. We need to understand how we make electricity in the first place, and, more importantly, the fundamental problem that engineers had to solve right from the get-go.
At its heart, it's actually surprisingly simple. An electrical generator is really just a machine that converts mechanical energy, something spinning, into electrical energy. And the two key ingredients, a magnet and a coil of wire. That's pretty much it.
Okay, so picture this. As the magnet spins, its north pole comes by and pushes the electrons in the wire one way. Then, as the south pole swings past, it pulls them back the other way. This constant push and pull creates a flow of electricity that alternates its direction, and that's what we call alternating current, or AC. The single complete wave of power you get from this one coil, well, that's what we call a single phase.
And this little experiment is just a brilliant way to see it in action. If you hook up two LEDs but you face them in opposite directions, only one of them can light up at a time. So as the current flows forward, the first one lights up. When it reverses, that one goes out, and the other one lights up. If you could slow it way down, you would literally see the current changing direction, back and forth, back and forth.
So here's the crucial point. With just one phase, the power isn't steady, not at all. The voltage rises up to a peak, but then it drops all the way down to 0 before rising in the other direction. This creates this pulsating, inconsistent power delivery, which, well, it isn't ideal for pretty much anything you want to run.
So how do you fix this pulsing problem? Well, the solution is just pure engineering elegance. Instead of trying to reinvent the wheel, engineers realized they could just add more of what was already working. They just added more coils.
And the improvement is just dramatic. With one phase, you get that big pulsating drop all the way to 0. Now, adding a second coil helps, for sure, but you can see there's still a noticeable dip in the power. But when you add a third coil, the power becomes almost perfectly smooth and constant. And that's the goal.
And the key to making this all work so perfectly is geometry. It's beautiful. The 3 coils aren't just placed randomly. No, they are positioned precisely 120 degrees apart from each other around that spinning magnet. This perfect spacing ensures that just as one phase's power is starting to dip, another one is rising up to take its place, creating that beautifully stable, continuous output.
So this naturally leads to a question, right? If 3 is good, wouldn't 4 or 5 or even 6 phases be even better? Why do we stop at 3? Well, it all comes down to a classic engineering trade-off. While, yeah, you could add more phases and get a tiny bit more stability, the costs and the complexity would just explode. You'd need more wires, way more complex equipment, and trying to balance the entire grid would become an absolute nightmare. 3 phases just hits that perfect sweet spot. Maximum stability for minimal complexity and cost.
But the genius here doesn't stop at just generating the power. The next brilliant step was figuring out how to wire this whole 3-phase system for maximum efficiency out in the real world.
Just think about it for a second. 3 separate coils. That should mean 6 wires coming out of the generator, right? A pair for each coil. Can you imagine the cost of running 6 massive cables all the way across the country? But because those sine waves are so perfectly offset, engineers found a way to cleverly combine the return paths, which cut the number of wires needed from 6 all the way down to just 3 or 4. I mean, that saved billions in copper and construction.
Now, there are 2 main ways to connect these coils, and they're named for their shapes. Delta, which looks like a triangle, and Y, or star. Delta is this simple, powerful setup that's perfect for huge industrial motors that just need raw 3-phase power. But for our everyday world, the Y connection is the real star of the show because it adds a crucial 4th wire, the neutral.
This neutral wire is the absolute secret to our modern grid. It gives us a stable 0-volt reference point. But even more importantly, it allows us to just tap into one of the 3 phases and connect it with that neutral. And that, right there, is how we get the single-phase power for the outlets in our homes, all from a larger, much more efficient 3-phase system.
Okay, so we have our efficient 3-phase power. Now what? How does it actually make that long journey from the power plant all the way to your wall plug? Well, that is the job of the massive electrical grid.
Right at the power plant, the voltage gets stepped up to incredibly high levels for its long journey across the country. And this is done for one simple reason: efficiency. Pushing high voltage allows for lower current, and that dramatically reduces the amount of energy that's just lost as heat in the wires. Then, as it gets closer to your city, it's stepped down at substations. And finally, a transformer near your house brings it down to a safe level, tapping off just one of those phases for your outlet.
But that brings us to one last little mystery. We've established that the voltage is a constantly changing wave, right? It's going up and down. So why does a multimeter show a steady, constant value like 120 volts?
This simple analogy just captures the practical benefit of all this engineering perfectly. A motor running on single-phase power is like one person trying to push a heavy wheel. It's going to be jerky and really inefficient. But three-phase power is like three people pushing that same wheel in a perfectly timed sequence. The result is smooth, constant, and incredibly efficient rotation. This is exactly why factories and big data centers rely on it. But that still leaves the question: if the power is a wave, what are we actually measuring? That steady number, that 120 volts we all talk about, is called the RMS, or root mean square voltage. It's a really clever way of finding the effective power of an AC wave. Essentially, it answers the question, what DC voltage would I need to produce the exact same amount of heating power as this constantly fluctuating AC voltage?
And the name root mean square literally describes how you do the math. You take the voltage at every single point in the wave, you square it, which gets rid of all the negative values, then you find the mean, or the average, of all those squares. And finally, you take the square root of that average. The result is that single useful number that represents the effective power of that constantly changing wave.
So, the next time you flip a switch, you'll know about the perfectly balanced three-phase dance that's happening behind the scenes. And it really makes you wonder, doesn't it? What other incredible, invisible feats of engineering are hiding in plain sight all around us every single day?